Hi everyone, welcome to the Next-Gen SDN tutorial. For those of you just wandering in, if you don't already have a tutorial VM, just raise your hand and Carmelo or Yi can help give you a USB stick. If you downloaded the VM already from the internet, or you're getting it off the VM, off the USB stick, we still recommend that you update to the latest version of our dependencies. So follow these 3 commands at the bottom. We'll print these again before we start the exercises, but you can get this started now, which will save you some time when we get started later. So the first thing is just going to pull the latest version of the tutorial starter code, and then the second command, make pull deps, is going to pull down all of the Docker images and Maven dependencies that you'll need to run the exercises. So just you want to talk through this now?
Well, it's just a reference to use it during the exercises.
So during the tutorial, if you open up this set of slides, you can find a link to them here, bit.ly NG-SDN tutorial slides. So if you want to follow along or follow later, you can actually get this copy of slides that we're using here. And when you're doing the exercises, if you're curious about what the topology we're using is, all 4 of our exercises use the same topology. There's 4 switches, 2 spines, 2 leaves. This is a 2x2 leaf spine fabric. We have 3 hosts connected to the first leaf in the first IP subnet, second host in another IP subnet connected to the first leaf, and then 2 other hosts in 2 different IP subnets connected to the second leaf. So you'll maybe refer to this later when you're trying to figure out the topology we're using. All of the switches in this topology are going to be based on Stratum, which we'll talk about in just a bit. And the hosts are emulated hosts using Mininet. So your instructors today are myself. My name is Brian O'Connor. I work at the ONF and lead the Stratum project. And our other instructors, Carmelo, Cascone, who also works at the ONF and has been largely leading the controller side of Next-Gen SDN. So the implementation of the Next-Gen interfaces in ONOS, as well as a lot of development in P4. Just a quick overview of our schedule. So we're currently in the overview section. So we're just going to provide a brief motivation for what Next-Gen SDN is, and also a little bit of a primer on Stratum, because that's one of our newer projects. Then we'll spend our first block doing the P4 and P4 runtime overview. We'll have a few hands-on to solidify some of the concepts. We'll take a break and then do the configuration and management side. We'll talk through Yang, gNMI, and OpenConfig. Then have lunch. After lunch, we're going to actually connect ONOS as our control plane for the afternoon exercises. And then in the last session, we'll just do some more advanced work, writing some ONOS apps and looking at other use cases. So let's get started. So for those of you who have kind of been following SDN for a while, you may be familiar with SDN sort of version 1.0, the SDN of 10 years ago. And this SDN was kind of revolutionary because it was one of the first times we had an introduction of programmatic network interfaces that were optimized for machines to communicate with networking devices over a management network. For the data plane, we could program the network using OpenFlow. And for configuration and management, we had the Yang modeling language and netconf as a protocol for interacting with devices. The promise here of SDN was to separate the data plane and control plane so that they could evolve independently and didn't have to run on the same hardware. So we had packet forwarding devices, which made up our data plane units, and we had a network OS that could run independently. But if you kind of followed along, there were a few problems that people encountered as they started to implement some of these solutions. So first, a lot of the programmatic network interfaces were inconsistent. So OpenFlow, for example, didn't provide a data plane pipeline specification, which packet headers could be parsed and which tables they could be put into. Every vendor provided their own models for configuration and management, and there were differences in protocol implementations that required custom handling in the control plane. So effectively, we had solutions that were tightly coupled rather than independent. And so in reality, a lot of control planes were written, but they were tested against specific hardware. They weren't general purpose. Some control planes worked around this by building their own abstractions to handle these differences. For example, ONOS used something called flow objectives, which kind of used an underspecified pipeline definition that we tried to map down to real hardware. Or others used a more least common denominator approach, like SCI is an example, switch abstraction interface, of a model, a pipeline model that's relatively simple, but common across a lot of targets. Other control planes effectively are typically built directly against vendor-specific APIs, and that locks them into those vendors. The other piece to this was shortly after SDN, there was a revolution in network functions called network function virtualization, where we migrated from specialized networking hardware like firewalls, load balancers, NATs, to commodity servers. And these virtual network functions are packaged and distributed as VMs or containers, which are easier to deploy. And we could be more efficient about the hardware that we use to implement network functions. Same as the revolution in virtualization for compute. But this, too, has had some problems when we've tried to put it into production at scale. For one, CPUs are not the right hardware for many network functions. Latency and jitter on CPUs are a lot higher than some of the alternatives, like FPGAs or ASICs. And the per packet cost of sending packets through a CPU is also higher per bit, as well as requires more power. So if you're really trying to scale up, a lot of network functions are not well suited for CPUs. Furthermore, to make matters kind of even worse, a lot of initial implementations of NFV were fairly naive about their topology. They just used the same networking stacks that were used in things like OpenStack and Kubernetes, which means they're kind of inefficient if you're trying to process a pipeline of network functions. These extra switching hops to implement sequences of VNFs are quite costly, and it can sometimes require you have a packet traverse the network multiple times for each hop. When you combine the two, a lot of people use SDN to implement their fabric. NFV was kind of the overlay where they did service chaining or end-to-end service delivery. And these two solutions, in many cases, were managed separately. So we have an increase in operational complexity. It's difficult to optimize between these two stacks because it's not necessarily clear what the interface between them is. And then if you're trying to do end-to-end optimization or end-to-end troubleshooting, it's difficult for us to do that because we have to go collect information from two stacks and combine it together. We also have kind of an over-provisioning of resources because we need to have resources available for our networking stack and our NFV stacks independently. So overall, I think there's been a lot of benefits and a lot of network evolution that we've seen as a result of these architectures. But there's also been significant cost to them as well, which I think in many respects has hampered their ability to be deployed on larger scales. So some of the obvious questions you might be asking, can we get the benefits of SDN and NFV without paying these costs? Can we incorporate some of these lessons learned from production deployments to improve our initial architectures for SDN and NFV? And is this architecture set up, or can we build an architecture that's set up to take advantage of new networking hardware efficiently and rapidly? As we get 400G in the data center, as we get new programmable ASICs, as we get new SmartNICs and FPGAs, can we take advantage of these things quickly? And this is where next-gen SDN comes in. It's our next generation of these architectures. And it's largely built on a substrate of a few components that the ONF has been working on. The first is forwarding devices. So in next-gen SDN, we want to mandate a forwarding plane or a forwarding pipeline to the switch. And we do this using a language called P4. We've also done some work to support existing ASICs, like fixed function ASICs, and partially programmable devices to enable a smooth migration from our older network generations to the next generation. Next, we have a switch OS called Stratum. We call it a thin switch OS because it does not come with a bundled control plane, no BGP, OSPF, et cetera. It supports a next generation of network interfaces called P4 runtime, gNMI, and gNOI. And it still supports the same Yang models as before. And we've selected a set of OpenConfig models that is common across all Stratum-based devices. Lastly, we have ONOS, which we've upgraded to support the next generation SDN interfaces. We've also made a move from the older deployment model to a newer deployment model where you can use microservices to deploy ONOS, as well as more modern cloud orchestrators like Kubernetes. This enables applications to take advantage of the new data plane capabilities. Zooming up just a level, we can kind of look at the big picture. So SDN is kind of revolutionary in the capabilities that it provides. For example, top-down programmability, rather than kind of reading and adapting to a bottoms-up definition. This enables us to do things in a hardware-independent way, unlike most solutions have been in the past. A big shift in here is also a learning that zero-touch capabilities or automated lifecycle management is important. Having humans configure these boxes and manage updates doesn't scale when you put this on tens of thousands of switches. So we need to have efficient machine-readable interfaces, both on a protocol level as well as a data modeling level. And finally, this leads to an ability to be more explicit in the way we verify our network. So we have some kind of a revolutionary architecture, but an evolutionary roadmap. So to achieve these capabilities, we can take a few steps to get you from the initial versions of SDN and NFV to our next generation. So first of all, we have the interfaces already defined. P4, P4 runtime, OpenConfig, gNMI, gNOI. They're all on GitHub. You can download them, look at them, read the specs today. Stratum is going to be released this week as part of the event into open source. ONOS 2.2 was released a few weeks ago, and it supports next generation APIs. So it supports P4 runtime, gNMI, and gNOI. We've established a tool of cloud native capabilities for orchestrating the next gen pieces. And we're just getting started on how to use all of this to verify your network. So the next piece is what is Stratum. So ONOS you may be familiar with. If you're not, Carmelo is going to provide a quick overview later. But Stratum's an open source production targeted thin switch OS that implements these interfaces. And so in Stratum we have a few things. The first thing is Stratum's built on hardware typically. So we have switching chips and peripherals that expose their own SDKs and their own APIs. Stratum runs on Linux, so we put Linux on that box. And then on top of that, we have abstractions that map the runtime APIs, P4 runtime, gNMI, and gNOI, down to these platform-specific APIs. We also have P4 compilers that are used to map resources on the ASIC or provide the mappings from the P4 runtime to the switch SDK. And then a set of test cases and a device under test or switch under test runner to make sure everything is compliant. So Stratum, one way to think about it is it's an implementation of the next-gen APIs on the data plane. So for control, this is where we've used OpenFlow in the past. We're now using P4 runtime with a P4-defined pipeline. So this is how we manage the match action table entries and other forwarding pipeline state. For configuration, this in the past has been SNMP or netconf or resconf. We're using gNMI with a set of OpenConfig models. So this is how we do the configuration of everything that's not the forwarding pipeline. How we set port speeds, read port counters, manage fans, configure the SFP modules. And then for operations, which historically has been telnet or SSH and running some commands on the terminal, we're using gNOI. And this is how we do things like reboot, pushing SSL certificates, diagnosing port problems, et cetera. All of these APIs are defined in gRPC and protobuf. How many people have heard of gRPC? Leave your hand up if you've used gRPC. OK, so a little over half have heard of it, and less of you have used it. So you all use it by the end of today. But I think it would be helpful to just provide a quick primer on what it is. So gRPC is a recursive acronym. gRPC, remote procedure call. It uses a schema format called protocol buffers to define the service API and the messages that go over the wire. And you can automatically generate client and server stubs in a whole host of languages, including C, Python, Java, Go, etc. Under the covers, we use HTTP 2.0 and TLS to establish and secure our connection. And we can use a single TCP connection to support multiple calls, multiple parallel client calls, as well as multiple services on the same server. If you haven't seen or heard of protobufs before, this is kind of the first step to understanding how to write a gRPC service. So protobufs comes from Google originally. It's their lingua franca for serializing data. This is useful for RPCs as well as storage. There's a textual representation of protos that are useful for debugging, but really, when you're using them in production, these get serialized to a binary format. Structures are extendable, and they, by default, support backward compatibility. And you can generate objects in native languages, like programming languages, for even more languages than gRPC supports. It's strongly typed, so things have an explicit type, string, int, bool, etc. And it's not necessarily required for gRPC, but almost everybody pairs gRPC with protobufs. So on the right-hand side of the screen, we have an example of a message called person. This is what you consider like a struct or an object in most programming languages. We can have explicit members of that message, like a string name, int ID, or string email, as well as support for enums. And you can also put together arrays of these objects or use messages within other messages. They stack hierarchically if necessary. So we can also use protobuf to define our gRPC service. So we define a service named greeter. We can have a method or an RPC on that service called say hello. And then every RPC in protobuf takes a single message as an input and returns a protobuf message as an output. So in this case, our hello request is a message that contains one argument or one parameter, the name, and then it will return a message that has one parameter called a message. So we use protobufs to define our message format. This is how the data gets encoded and serialized on the wire. And then we also use protobuf to define our services as well. And so for each of the next-gen SDN APIs, you'll see that there's a definition where we have a service portion as well as messages that are used on the wire. So a big question we get is, how do we achieve ASIC independence with P4? And so we start with a P4 program. For example, this is a simple P4 program where we do routing classification followed by IPv4 ECMP or layer 2 forwarding, depending upon the classifier's decision. And then we have an ACL table to do redirect, drop, or packet outs if necessary. We first use a P4 compiler to generate a control plane contract for that program. This is called the P4 info, and Carmelo is going to describe a lot more of that in the first exercise. We also have the compiler allocate resources to realize this pipeline. So we can dynamically map from a P4 program down to a runtime mapping. And in Stratum, we support 3 different backends. One is BMV2, Behavioral Model V2, that we'll use in these demos. It's a software switch. We also have mappings to Barefoot's Tofino ASIC, as well as Broadcom's Tomahawk ASIC. These runtime mappings and P4 info feed into our data plane and control plane. The runtime mapping just goes to program the switch ASIC, and then the control plane contract is used by both the P4 runtime server, the implementation of the P4 runtime API on the device, as well as used by the client, which is the control plane. We also can achieve platform independence on the configuration and management side by using the same set of OpenConfig models. So OpenConfig provides a set of Yang models that define everything from interface configuration to components configuration, QoS, as well as configuration of higher level protocols. And what we do in Stratum is we have a gRPC server that sits on top of our OpenConfig mapper, which consumes and translates these models into an internal representation. It also is able to store some of the configuration as a tree, as mandated by the OpenConfig model schema. This sits on top of Stratum's platform manager, which then can translate the Stratum API calls down to Open Network Linux, our base OS's API, that then can be translated down to some of our vendor-specific implementations. So today in Stratum, we have support for, I think it's 9 different switches. We've got a range of Tofino and Tomahawk hardware switches. A lot of these are 32 or 64 by 100G data center devices. We also have support for 2 software switches, BMV2, which we'll use today, and Dummy Switch. And we also have some platforms we're expecting in the near-term future.
Sorry,
yeah, sure.
On the Tomahawk support.
Yes, we have a compiler for
the Tomahawk.
Tomahawk. Yeah.
Okay.
There are some limitations, and if you're interested in kind of how we do that, there's a talk on Wednesday in the afternoon that will go into how we build a compiler for Tomahawk. So the other thing is, how do we build and install Stratum? So there's 2 different ways that we've seen this done in the past. Traditionally, you take your drivers, your SDKs, and your OS, you plumb them through a big builder script, and you get out an image, a switch image that you can run on the device. And Stratum supports this model if you want. A more modern way to do this is you have your platform API and your Linux kernel build a base image, and then you take your SDK and your Stratum code and you push it into a Docker container. That Docker container sits in a repo, and then it can be pushed down to a switch. And you'll see in our demos later this week, we have containerized Stratum being pushed and run on the device. So you can basically rebuild your container image, repush it, and restart the device without having to reflash the OS and update everything. It can be a much more efficient and faster. The other thing that we mentioned is testing. So in Stratum, we have a test framework called test vectors. These serve as compliance tests for Stratum-based devices. Test cases can either be written manually, like we've done in the past, or we can generate them automatically. So you can write them manually and just push them to a repo. You can also use higher-level languages to, in a semi-automated way, generate a set of test cases. Or we can use like semantic analysis of our APIs and automatically generate a whole pile of test cases. There'll be a more in-depth talk on how we generate some of these by a few presenters on Thursday. So if you're interested in this, you can take a look there. But these test cases then get plumbed into a runner, which connects to a device using its gRPC interfaces. We also connect to a traffic generator and are able to validate that a device is conformant with the APIs that we have. So that's a basic introduction to Stratum and to NG-SDN. If it's a little bit overwhelming, this material is going to be presented throughout the conference in much more detail. But hopefully this gives you kind of a primer and some motivation to why we're here and what exactly NG-SDN is. So what are the goals specifically for today's session? And there's 4 of them. One is to give you exposure and experience working with P4 code and Yang code, kind of the basis for configuration modeling and pipeline modeling. The second is to give you an understanding of P4 runtime and gNMI, as well as to give you experience using CLI utilities to communicate with these devices, which is something you might do if you're just getting started or trying to debug a problem on a device. Next, we want to give you experience running ONOS and Stratum and having them connect together, configure them. And finally, we want to give you a little bit of experience writing a simple or modifying a simple control plane application that interacts with a P4-based device. Taking a more practical step of how we're going to give you that experience, our goal today is we're going to build an IPv4-based leaf-spine fabric using P4, Stratum, and ONOS. And to get there, we're going to have 4 sessions. The first session is P4 and P4 runtime basics. Second is Yang OpenConfig gNMI. Third is using ONOS to connect to Stratum. And the fourth is going to be modifying our P4 program and ONOS app to enable routing.